Today is Friday. October 30th. We're near the end of October, so you guys have I got one thing left, and that's Halloween. Also, be sure to set your clocks back this week. I think daylight savings time will end on Sunday morning, technically. Oh, physics 174. It's the 8 a.m. class, or it was at least when we got here. I'm trying to get this camera going. And page one. All right, so what's on the old docket? Well, let's talk about those exams. I want to keep mentioning those exams. So let me look at the calendar here. We have November 18th, 2020. Exam number 3, regular exam number 3. That's a Wednesday. 2 days after that, it'll be a Friday, and it's the makeup exams. So they'll mimic the regular exams in both nature and also just how they're given us. So exam number 1 was on Gradescope. I'll make makeup exam 1 on Gradescope 2 to reflect that. And there weren't as many problems on it, and that was always intended, but that'll also be the same number will be on the makeup. So it'll be 5 multiple choice and 2 partial credit. Handing them in your solution problems. Exam 2 makeup will look like what you guys had a couple of days ago, last week. I guess it's on Monday. It seems like it's forever now, and that will be 16 multiple choice questions. Somebody try to join. There we go. Admit them. And that leaves us with talking about the final. The final schedule just came out. I thought it'd been out, but it came out actually just yesterday. Now I know why I didn't pay much attention to it. It hadn't made it out yet. And they gave us a choice for what we wanted to do. We can either do in-class exams or we can do virtual ones. And a lot of you guys have already talked to me about how you got so much stuff piling up. And when I saw the final schedule, it looked like there were very few in-class exams. When I say in-class, it means it was held prior to November, or prior to Thanksgiving break, which is now going to be the end of the semester as far as in-class service stuff. So here's the plan. I put in for us to have a final on November 23rd, 2020. It's a Monday. And when I say in person, we've got the option to be in person. Some of you guys have also come back and said, "Oh, I just wish I could be, in the classroom with me or something like that. I'd be able to ask questions, be easier." Some of you prefer your own home. Some of you cannot prefer anything else because you're not anywhere close to this campus right now. But I thought at least give you the option, because let's face it, if you're virtual, you're going to have the same option as before. Or you can stay on your campus dorm, you can stay in your house nearby, or you can actually come in and be with me. So I'm planning on this to be the final date. Now the times have yet to be determined. To be determined, and not regular class hours. For you freshmen out there, I guess it's a lot of you, that would always be the case no matter what. We have an hour and 20-minute class. Finals last 1 hour and 40 minutes, if I've got that. Yeah, I'm pretty sure about that, about 100 minutes. So you can't fit it in a class time. And we might be able to start at 8 a.m., but we couldn't finish on time. And that would push all the other classes all out of sync too. They wouldn't even start and end at the same time. And so there's no guarantee we'd be the first final. We might be the last final of the day. And it's just the way it goes with finals. So it's not going to be during our class time. It might overlap some of it, but not all of it. Or maybe we'll overlap the whole thing and even extend into something more. So be careful about the date, scheduling anything like doctor's appointments or work or something like that on that date. There is a bonus, 1-point bonus quiz on Canvas. due by Saturday, tomorrow. I think I put 11:59. I think in the paper I put 11:55, but give me a little wiggle room there. 11:59 p.m. And the quiz question only asks, and like I said, it's not a quiz, it's just a survey basically, to see if you would like to take the final in face-to-face with me in this classroom, or if you're planning on doing it virtual. There's also actually a third option there too. When it comes to taking the class face-to-face with me, we have to do it still. It's going to be kind of crazy via computers because I've got to get the same test to everybody. Everybody had to go through Canvas or Gradescope, wherever, however we're going to do that. I'm still monkeying around or toying around with that idea of going back, partially back to Gradescope with a way to hopefully circumvent it. But anyway, if you've got problems with Gradescope and stuff like that, and you think I don't want to upload it, and if you're on campus, you can come in here and take the exam with me and just hand me your handwritten solution. I think I'll have something like that for the final. I'd like to have some kind of partial credit, or at least I'm trying to keep that open right now. All right, so be sure to just take the quiz. It's non-binding, but I also need to get a general head count. You know, try to answer as truthfully as you think you're going to do it. You can change later because I had to tell the registrar or the scheduling people how many people are expected in the final. And therefore, I can tell what kind of room I need. Can I get away with this room? We're doing a slightly bigger room because of social distancing. If you do come in person, it's the same rules as before. Open book, open notes. You can bring as much as you want. It will be a little bit of a hassle for you to bring a bunch of. If you like to do an exam with 20 textbooks around you, I can't imagine you go through 20 textbooks. But if that's what you like to do, that might be a little bit impossible for you. But if you just like to go through your favorite textbook or two and your notes, or something you can carry in a book bag and get it in this room, then you're completely welcome to do it. So of course you can also surf the web and consult anything that's non-living. You can't pose any questions to anybody, but you can surf if you want to. Once again, I wouldn't think you'd have much time for that to find your questions. But anyway, that's your option. If you do come in here, you can bring your own laptop, or it's one of the options on that little bonus quiz. You can request that I would get a laptop from the computer guys here on campus, and I'll have something ready for you. So just look it up. It's in, look under assignments. I think that's where I put it. It makes sense. All the way at the very bottom of assignments, the last thing, like it's due tomorrow, so it's the only thing on there right now with the due date. Right? So I'll have to change that very soon, but not right now. Not anytime, maybe tonight or maybe tomorrow. All right, so that's it. Any questions on that? Nothing out there. All right, so what we're doing, from Wednesday, we found work done by a constant force to move a mass m a distance delta r. That's really displacement. A little vector above a little arrow is work equals F delta R cosine theta, where theta equals a smaller angle between vector F and delta R. So you're moving this object mass here. Let's put the mass here if you want to see it. If it's going to slide in this direction and you're applying a force in this direction, you think, well, there's no way it's going to do that. Well, it can. Like I said, it can be in a track. It could be confined to some kind of, maybe you're it's not going to look too good here, but it could. Maybe it's sliding down a ramp and you're pulling on a rope or a handle in this direction. So you don't pull an object, down a ramp with a force that parallels the ramp. That'd be very, very awkward unless it's a big box and you get behind it and push it. But even then, you're probably gonna get some angle. Or what usually happens is we've got multiple forces acting on the object, this is what you're doing. We're always very interested in how much work do I have to do? That's always the concern of ours, right? How much do I have to put into this problem? How much labor do I have to do? So we just want to know what my work is involved in this process. And there's other things going on, and maybe the combination of all the forces results in this direction. And this is your angle theta. Right? So there's a worksheet that's at the bottom of Canvas. Well, it used to be at the bottom of Canvas. Now it's no longer quite at the bottom, but it's in that last module down there. Hopefully it is. You guys are going to tell me, but that was the intention. And it starts off with this little problem right here. And there's lots and lots of problems, but these are, we're going to do the work for constant forces. So we have, I think, 3 of them, right? We have 3 of them. We have 3 of them. So let's do problems 1 through 3. Give you about 10 minutes to do them. Of course, you can always come back with questions or something like that. Break in and unmute your mic and ask me something, or you can give me a chat. Otherwise, there we go. Let's go. Let's do some problems, and we'll talk about those, and we'll continue on with how we what other things, other ways we can find work. Right? Ding. Clock is ticking. All right. 8:30 now. No questions, huh? I guess you guys are getting all these. I'll do a couple and we'll just jump on out of there. It's easier than I thought. Great. Great. No questions, no problems. All right, so let's at least look at a couple of them. No need to run it into the ground. Get them. I guess this will be page 2, actually. This. So here's the first guy. Find the work done by various forces that are acting on this mass, which is being pulled at a constant velocity, 4 meters per second to the right. So what do we got here? The key thing is we know it moves 5 meters in the direction of velocity. So it just tells us this thing's going to end up over here. Five meters. That's your delta R. That's just your display, or that's your distance traveled, not your displacement. Your displacement would be represented by an arrow. Oh, there we go. Again, make the arrow like that. There we go. Now, length of the arrow represents the displacement, just remember the distance it actually travels, and the direction of the arrow is your direction. All right, so there's asking you how much work's done by these various forces. I only see one force here, but it's like the force diagrams. We got to go back to those. So we have to draw our forces. There's a normal force. There's Fg, aka your weight, n times g. And since it's moving to the right, the frictional force will be trying to stop that motion, so it's going to be pulling to the left. All right, so in every case, work equals force times a, I'll write force here because if I write F, then there's that little F there, so I should have put him as F1. So it's a force times a delta R, your distance traveled, times cosine theta. And like I said on Wednesday, we have to go through this equation for each force, inserting the magnitude of the individual force and the angle that force acts relative to delta R, your displacement. There's a good chance all thetas will change, and here there's actually going to be 3 different thetas. And the force also, the magnitude of the force also is going to change too, most likely. And delta R, though, stays the same. All these forces are acting on this box at the same time to produce this. And how do we know this? Well, usually that's the case. So I'm going to say, you know, it's not what can happen in reality, and we can actually make a problem quite very easy, a 2-step problem where at one point one force just drops off. Maybe this force here stops. You know, you increase your force, maybe you decrease it. And then you can talk about what's going to happen there with the work done by that force when it changes. But we're talking about constant forces. So hence, we're going to keep all the forces constant in this area. Next week, we'll start changing them around. But you can tell this is a constant force problem because the velocity is constant. The velocity is constant means your acceleration is 0, which means the forces acting on it have to sum to a constant value. Actually, there would be no, the force sum would be 0 because there's no acceleration. All right, so here we go. As for the normal force first, so here's A. That's what it would look like for just a generic equation, the normal force magnitude times delta R times cosine theta n. Now, if you remember your force tables, the normal force will not equal mass times g because we have this force here pulling up on it. But I never would figure out this force first. I would always, the first thing I find when it comes to the work problems is the angle. In this case here, we have, I'll draw them individually, case per case. The normal force points up along the vertical y-axis. The vertical x is where it's moving in the direction. And since it's moving in the positive x direction, this is also going to be the direction of your delta r. So here's your theta n right here. See about there, want to guess what theta n is going to be? If normal force along y and displacement along x. Thanks. 90 degrees. That's absolutely right. You might know what cosine 90 is. Get your calculator out and punch it in. Cosine 90. This is why I never figure out the force first. I always figure out these angles. That's right, 0. So work equals Fn delta R. I'll put in delta R. It's always going to be the same, but I'm not going to work too much with it and worry too much about it because I get cosine of good old 0 degrees. And this guy is equal to the big old goose egg, 0. So I guess I should have started, my bad. Work done by the n, the normal force equals 0. I had that for an answer. So you can figure out the normal force if you want to. It's good practice. Maybe we'll need it for the frictional force or something like that. But the when it comes to actually figuring out this work from the normal force, it was useless to do it. We will need it for the frictional force, but we don't know we're going to need it at the moment. So always figure out the angle first. If you're lucky, it's a cosine 0, and you're off the hook for making the calculation. Or sorry, cosine 0. My gosh, cosine 0, my bad. Cosine 90 degrees. There we go. 90 degrees. Plug in 90 degrees. Or cosine 0 is 1. So cosine 90 is just going to give you the big goose egg of 0. Right? So, and it makes sense by what I said on Wednesday. Let's face it. If you're trying to move an object to the right and you're pulling on it straight up, which is the direction of normal force, this guy right here will not help you at all move this object horizontally. He only pulls vertically, so he can't move it to the right or left. That's reflected by that answer. You might be able to guess really fast what's going to happen to good old work, or sorry, the gravitational weight. The weight pulls straight down. So he pulls vertically downward. We're trying to move it to the right. This guy should do no work as well. Work done with the gravitational force. Let's call it WG equals FG delta R cosine theta G. And it's a good practice to do this guy because you get used to these angles. FG equals MG. And in the old days, we measured the angle all the way around. That. But not for work. Work, we want the angle between the force and the delta R. In other words, between the two vectors. So we want this angle. And since delta R is horizontal, going to pull to the right, and our weight is pulling down along the negative y, this guy also equals 90 degrees. And you're not wrong to say, mathematically, you're not wrong to say 270, but we stick with a smaller angle. It won't burn us here for, it won't burn us in this with cosine, but it will burn us later on if we get to torque. We have to talk about a similar equation, but it has a sine theta in it. So here we go, WG equals Well, we could just leave this guy completely blank, but let's make sure, remember, weight is m times g times your 5 meters, so same delta r here, cosine 90, and that's just going to equal 0 again. So I don't even bother figuring out what the mass times g is. Now, dang, I need more room. Okay, so we're going to figure it now for the 25 Newton force. So let's see if that one. If Newton's going on this angle here at 35 degrees. And this is my delta R. So here's a case where delta R actually is along the x-axis. So we are measuring an angle technically from the x-axis, but that's only because delta R falls along the x-axis. Didn't have to be so. Definitely why I didn't lead off with that example when I first did a work equation. It's nice when you see it, but you know, it doesn't have to be. And that was the first equation, our first example, only example we did on Wednesday. So work done by big F equals F delta R cosine 35 degrees. And we can imagine this time we're actually going to find out that we're actually going to get non-zero work, and it makes sense. Our force is pulling along delta R, at least it's got a component along delta R. So he's the guy actually making it go to our right now. So we're going to put in his magnitude, 25 newtons times 5 meters, cosine 35, and lo and behold, hopefully, we get 102.4. Let's just I round it to 102 for the answers. So let's keep it that way. And that's definitely 3 sig figs. It's more than that question actually. Well, yeah, it's exactly the right number. 20, we had 25.0 Newton for the force. Oh, but no, that guy only had 2 sig figs. I guess that's still a little too much, but that's okay. Closer and closer to reality what it should be. And finally, the last guy worked under the frictional force. I'd write a little W, W is a little F right off the bat, but since I've got the big F up here, it might look like, hey, it's the same F all of a sudden. So if I write W friction, you know that I'm not talking about that guy. So if you went through this with C and this is D, that's a lot easier. And here we have delta R going that way, mass, and we have the frictional force pulling that direction. So right off the bat, I gotta get my angle, and that's 180 degrees. Call it theta little f. So you start with the same equation every time for a constant force equation. So it's just gonna be the frictional force now, it's magnitude, times delta R, times cosine theta f. Well, the frictional force isn't given to me, so I better have some kind of equation for it. So, well, normally I'd put mu Fn, that'd be my gut instinct there, cosine theta f. But I find out actually I don't have a, there's no mu given. So what am I going to do with this? Right? I don't know mu given. So what are we going to do? I'll recall V equals a constant. So acceleration equals delta V over delta T, and that's to be 0 in this case. And this leads to this fact. So the force in the x direction equals max equals 0. And what forces do we have in the x direction? I'm not going to draw the normal force and the gravitational weight. Those are all vertical forces. They have no x component at all. So the only guys who have x component is 25 newtons cosine 35 degrees. And if you want to call it this, we can just say the plus the frictional force times cosine 180 equals 0. We can solve for the frictional force now. So I didn't need to know the mu, actually. In this case here, the way the force table lines up, I can actually solve the frictional force based on Newton's second law. So it's a nice little way to always, sometimes you don't have to know the mu. So I just want to throw that out there. A way to find the frictional force using Newton's second law. So the frictional force is negative, and I gotta get this guy on the other side, negative 25 cosine 35, so it's not that bad. The frictional force, I'm out of room. A new piece of paper just for a couple lines. So the frictional force is 25 cosine 35. Which means I run back to my equation where I got stuck there. I can plug in the numbers. I do this. I get that other answer. So my frictional force is exactly opposite of the force that I'm pulling with. And that's why it's not speeding up. And that's going to be kind of an important thing to keep in mind, or at least we got it makes sense, which I hope it kind of makes sense. If you're pulling an object, and because that means you're putting an unbalanced force on it, it seems like. So therefore, by Newton's second law, it should speed up. It should have an acceleration in the direction you're pulling. This one doesn't. So that means there's got to be a counterbalancing force, which is negating what you're doing. It's not stopping you. It's just stopping you from speeding it up. So once you get it moving, frictional force is there. Your guys are at loggerheads. You guys are basically tied. And so you're putting in this amount of work. You're trying to speed it up. And frictional force is robbing you of this work. This is doing this negative work. It's robbing you of energy. It's trying to slow it back down. And as long as these guys are equal to each other, you can move it, but you can't speed it up. And so when we talk about the energy conservation theories, keep that in mind. It makes sense that friction is going to do that to us, right? So that's that guy, big long guy, but actually little bitty equations. Just got to make sure the warnings, I guess, are choose the right, or calculate the correct angle for each case. Okay, and that's definitely the big warning. I think you can probably get through the forces. The frictional force looked a little bit daunting there. We didn't see the mu, but showed you how to do it. So hopefully now you can put that in your arsenal of other ways to find the frictional force. Sometimes you don't always have to go through mu FN, even though that's a common way to do it. All right, no question on that guy? A lot of people responding out there. Let's do one more. Let's move on in life. I'm going to do one, and it's let's see, which one should I do? Should I do 3 or should I do 2? Oh, 3 is more fun. Hey, you want me to do 2? Is that what you want to do, Adam? 2? I can do 2. Sure, why not? Okay. I'm not going to have as much fun. That'll work. Let's see. My number 2 at. Paper. How about that? Where's that? I can't find number 2 because it's on the back of that page right there. That's why. So that explains it. I'll just get a piece of paper. Several of them. Okay, we'll do number 1. Let's go over there. Oh, I can't grab it. should have printed out individual papers. All right. Number 5, page 5. I should have printed this out landscape. Okay, so this problem here is and this is, if you can do this one, you can do number 3. I was going to do number 3 on it because number 3 had one angle you can probably get really fast. So this one here, we're just going to get redundant, which is great. We'll do the long guy first, or do the long guy, and we'll leave the other guy for you to figure it out if you haven't already. Now we'll just do it, and I'll get my sales pitch at the end of it. All right. So we have an object moving from the origin to the final position. Now this isn't delta R. It's going to turn out to be delta R. That's just by luck. On Monday I should make one here where it's not. And this is our final, and it's doing this because there's a force acting on it, and that's the only force we know acting on it, and that's period. If it's not, there's nothing else given here about other forces, and it's not like the other equation where well, we knew we had a mass. The object had a certain mass. So this is the force. If you want to the net force acting on it, how much work is done by this force? Well, the easy part is just writing this down. Work equals F delta R cosine theta. So we need the magnitude of F, we need the magnitude of delta R, and then we need this angle between the two. We can get kind of an idea what this looks like. It's good. It's great to sketch it. I highly recommend sketching these guys. The force has a positive X component and a negative Y component, so it's going to be somewhere in the 4th quadrant. And its X is bigger, or sorry, its Y is bigger in magnitude than its X. So it's going to, if I just roughly draw it, completely roughly, and I'm going to kind of, if anything, I'm trying to exaggerate it because I want some room to work here, at least for a while, and I still may have to redraw it at the end. Make it too tight here. So there's my force down there. I need the magnitude of it. So for one thing, I can just quickly, I can't go anywhere. I don't have any numbers here to stick in here. I need the magnitude of the force. And we did this on Wednesday. You use Pythagorean's theorem. There is a blown out, gory 3D detail. So Fx is going to be that. You'll love it when it's got X or I hats and J hats and K hats because the components are all written out for you. And there is no Z component, so it's a big 0. 2 squared. If you want to keep the -3 there, good. The math guys will like you. But remember that negative sign will not survive this process. And don't ever have a subtraction in there. Somehow you forgot about it. You squared the 3 and kept the negative sign. Don't do that. Now this is 4 plus 9 equals the square root of 13. I'm valiantly trying to keep this on one paper. It's not going to work. No. There we go. I've got my first piece of this puzzle I need. Right there. Now delta R. This is, I'm going off the page. This is our final. Delta R, start with the vector first, and I'm going to do the same game. Once I get the vector, I'm going to find the magnitude of this vector like I found the magnitude of vector F. It's R final minus R initial. Now, R final is given. This is where it ends up. And R initial isn't really given its numbers, but it says it starts at the origin. So it starts at the origin, and this is just zeros. This problem started at origin. So if I can remember, I'll try to make a problem start off on Monday where it doesn't start at the origin. The only thing you gotta do is just where does it start at and subtract out your initial from your final. You know, if you start at 0 and you walk 5 meters, how far have you walked? Well, I've walked 5 meters. If you start at 2 you know, on the number line x equals 2 and you walk to the 5, well, now I got to take 5 minus 2, and I've only walked 3 meters. So we can handle that, but you got to be careful, man. It'll be pretty obvious. I mean, it's either probably going to say something like the origin, or it's going to have this an x initial, and it'll be like an x naught or xi with some numbers after it. So it shouldn't be too hard to pick up on the fact that, uh-oh, I got to subtract out some non-zero numbers. So yep, because we start at the origin, our delta R is equal to our R final. So that's just because we started, and usually we start at the origin, so it's not like doesn't have to be. Once you got that guy, we need its magnitude. So it's delta Rx squared plus delta Ry squared plus delta Rz squared. 1.5 squared plus -2 squared. And that's the square root of 6.25. You're more than welcome to keep that in decimals if you want to, but I mean, that's a nice one. That's 2.5. Square root of 13 isn't nice. It's a big long thing. You have to round it. So if I keep these as radicals as long as I can, I'll avoid having any kind of problems with rounding errors. You know, if it's too much, but it just makes it a little. If I get 8.979, I can worry about that. Oh, it's because they're rounded. All right, so now we've got a lot of the puzzle here. So work equals square root of 13 times the square root of 6.25. I still got to get the angle theta. So I have to know where delta R is at, which, you know, this guy here is 1.5 I hat minus 2 j hat. So in other words, he's also actually in the fourth quadrant. Let's just skip to another piece of paper here. So there's B, need theta. And run back and I can solve my problem. Highly exaggerate F now. It's not that steep, but delta R is going to be somewhere like that. Okay? And the angle we want is, this is what we got to keep our eye on the prize. That's the angle theta, right? How are we going to get that? Well, we can get this angle. That's theta F. And how do we get theta F? Well, it's the good old days. Theta F equals inverse tangent. If you know the components of a vector, you want to know the angle, you just take the inverse tangent of its y over its x components. So if you look all the way back up here, this was given to us. We already knew these values. Fy over fx. Be careful, our calculator is probably going to try to lie to us a little bit, but it's okay. We're on to it now. -3 over 2. Theta F equals 1.5. The calculator says -56.3. I'm going to round it now by the calculator. That gives us that angle. I want that big red one. So remember, I got to add 360 to this guy. So that's theta F actual. I play the same game with getting the angle for delta R. So I want this angle. All the way around the rows here. And theta delta R is done the same way. We've calculated out what delta R is, displacement. Oops. Theta delta R equals inverse tangent, y component for a delta R, and the x component for a delta R. was that? Well, remember delta R to have to be our final, so there it is. -2 over 1.5. And this is -53.13 degrees by the calculator. But you can use these angles. This will still give you the right answer if you know how to finagle them. But I'll pick my way I'm going to do it. I'm going to convert this back into the proper angle from counterclockwise. And theta delta R actual, and we add 360 to it. Exciting, exciting, exciting. There we go. So I want theta. And if you look at the drawing up here, what's theta? Well, theta is going to be the difference between theta delta R and theta F. In other words, if I take theta F, I go all the way around and I add theta to it, I get theta delta R. Theta equals theta delta R minus theta F. It's going to equal 306.87 degrees minus 303.69 degrees. And theta equals 3.18 degrees. Very, very small angle. So there's not a lot of, basically they're almost around top of each other. Which means actually we'll get a lot of work out of good old force F because it's pulling almost exactly in the direction of delta R. But we didn't know that when we went into this. You know, I mean, you kind of eyeball it, so well, it's in the same quadrant, but how close is it? And going back to B, we can now answer the question: how much work force F for this function this force does? What was it? Square root of 13, square root of 6.25. Cosine of 3.18. That comes in 1,000, 100,000. Ooh, that's out to about 1/1,000,000th of a decimal. That's 9. So that's it. The lion's share of that problem, of course, was figuring out that, well, you can just look at it, was most of it trying to worry about that angle. I mean, the other guys, I think I worry about delta R, but that wasn't that bad. And we take two magnitudes of two vectors, that's not bad, but we had to figure out this theta, which is the angle between the two vectors themselves, and that was a little bit of a pain. And that should be the that's my lead in. Wouldn't it be great to be able to do this without theta? And you're in luck, because there is a way to do it. So I'm going to leave good old number 3. If you can do this one, you can do number 3. You can get back to me and I'll show it to you, or post it or something like that, but it's just redundant. No one's really asking out there. So let's talk about a way to do this without having to worry about figuring out theta. Before we get into this. Another way to find work. That's with the thing called the scalar, also called the dot product. It's ironic because it could be called either way. It could be called the scalar product, called the dot product, but since it's called either way and everybody kind of likes it, we call it the scalar dot product. So it's like calling something, well, it's green, or it's also bluish yellow, because blue plus yellow makes green last I heard. So I'd be like saying it's a green, bluish yellow, and it's what we call being redundant. It's too much, you don't need to say it twice. And yet we do this a lot here. We call this the scalar dot product. I tell you the truth, I forgot which way the mathematicians like it. It comes out of mathematics. They probably split it both ways. This actually goes all the way back to chapter 2. I mentioned when we discussed vectors, that was chapter 2's area, the focus of chapter 2. Back in chapter 2, I said, I don't even know if I wrote it down, but I threw it out there. There are 3 ways you can use multiplication with a vector. Okay. And we covered only one of them. So the one we did. And I don't know if it was late August or early September now, did around September 1, was a multiplying a vector by a constant. So we just have like something like V1 equals 2V2. Ta-da, that was it. That could be a fraction as well. It could be a negative number. But we just multiply a vector times some kind of constant, in this case V2, and that was it. There are 2 other ways, and we're going to talk about way number 2 today, or going into on Monday. This is multiplication of 2 vectors. So I know there's 2 vectors up here, but I didn't multiply the vectors together. I just multiplied one vector by a constant. I got a new vector. You know, I got a vector twice as long as V2. I call it V1. But how about multiplication of actually 2 vectors together? And to yield a scalar result. And that's the scalar dot product. You can kind of get where the name scalar is going to come into, and the dot's going to come in a second here in case you haven't seen it before. The other one, let's throw it out there. I can say later, I have no idea we'll get there. In the old days, we would get there, just barely, but who knows in this crazy semester. It's a, let's throw it out there. You multiply 2 vectors again, but you get the thing, you get a vector out of it, and it's called the cross vector product, or the vector cross product. And in case I don't get there, that is torques. So can't get to, when we get to torques, we're going to discuss that. Page 8. I was a little too close to the board today. Okay. So why do we care? It seems to suddenly all of a sudden go back to these vectors. Well, the scalar dot product yields an answer that's in the form of magnitude of vector number 1 times magnitude of vector number 2 times cosine theta, where theta is the angle between vector number 1 and vector number 2. And this is a mathematical thing, but it should sound very, very familiar to us. Now, hey, sound familiar? Yeah, of course, it's work equals F delta R cosine theta. I'll just throw this out here right now. This, we can use it for work, but I hate to say it works, but it can be applied to any two vectors, no matter what they are. You can use what I'm about to discuss. We can multiply two velocities together if we want to. We can multiply a velocity and an acceleration together. It may not make any sense why we'd want to do that, but actually there is a point we can get to that. Actually, it may be useful for us, but we can do it with any vectors. Right? So I don't want you to think this thing only applies to work, especially if you go on in life or if you hit this in calculus class later. Think, well, hey, it's this scalar dot product only works for work. No, it doesn't. It works for any time we're trying to multiply two vector magnitudes together, and it's cosine theta. So it's a really powerful tool to have. You can get a lot from that. So if you go to scalar dot product, as we're going to find out, it works out well for work. You can get more out of it using all angle or using a lot of vectors or any vectors. Oh, a little more paper here. So over here and grab some more. There's a head right there. It's like tangent. I just use the tangent function for, to find the angle a vector makes. That is not the only use of tangent. I'm sure you used tangent long before you heard of what a vector even was back in geometry class. So it's a handy little function which just happens to work out for vectors as well. And same way with the scalar dot product. It works great for lots of vectors. It works for any vector, two vectors you want to, but it comes in real handy for us in this context of work. So I've got some nice words there, but I haven't shown anything. I haven't shown you what you can get with it. And definitely, since I said there's another way to figure out work without using the angle theta, then that must mean that there's another equation out there for work. And that's what we're trying to get to. We're trying to get another equation with this scalar dot product guy. Suppose we have two vectors. I'm going to make these guys 3D here. Real generic vectors here. Okay. So here's my two vectors. They're 3D. They've got x and y and z components, and they're just labeled that way by some constants, ax, ay, az, and so forth. So for the b as well. We define a scalar dot product to be on the right side. I'm going to say AB cosine theta. So that looks like our work equation. It's just a generic vectors, magnitudes A and B. And we need to give us a mathematical symbol, if you will, to a way to write it a little faster. And this is what they write. They'll write A, vector A, dot, looks like a big thick dot, like made of multiplication, times b, and this is where we get the name dot at. So we get the word scalar for this type of mathematical operation because it will yield a number, a scalar only. We get the word dot because of the mathematical symbol we use to indicate we're doing a dot product, or a scalar product. We put a big dot there. So over time, they'll call this a scalar product or the dot product. I just throw out scalar dot product now. It sounds cooler to say that. Right? So remember, the magnitude of A is just A, and it's going to be ax squared plus ay squared plus az squared, square root. And same way for the magnitude of B. Bx squared plus by squared plus bz squared. And this angle theta, once again, is the angle, the smaller angle between A and B. Oh, no way. The next one. That's okay. Yep. There we go. Oh, now it gets fun. Horrific. I don't know. It's a bad way to end a Friday. I don't know if we'll be able to get all the way through it. So I guess we'll have to pick it up on a Monday if I don't get through this little. I'm doing a little bit of a theory here. I'm just trying to make a proof. At the end, we want to box in something. We may not be able to complete that box until Monday. Recall the good old days of algebra. So if you had some x plus y plus z function, and you multiply it by another function, 2x plus 3y, let's put 4z, what would you do? Well, I'd have to take the x times the first term, the second term here, plus x times the second term of the second term, plus x times the third term of this second parentheses. I guess they want a quantity. There we go, quantity. I'm using term twice there. And then I go back and I add in y times 2x plus y times 3y plus y times 4z. And you get the picture here. Oops. Funky x here. Plus 4zx. And on it would go. Okay. Well, that's with I should call them normal numbers. That's with non-vector numbers, scalars. We've seen vector algebra. We can treat vectors just with normal algebraic rules. We can slide them around. We can combine like ones. We can divide by constants. So we can do algebra or we can do multiplication similarly. There's a little, it works the same way. So A dot B is just going to equal AX I hat plus AY J hat plus AZ K hat. And I multiply them. I put that little dot there so I know what I'm doing here. It's my vector multiplication for the scalar product, not normal multiplication quite, because these are vectors. And I would take AX, this term, times the BX, plus AX times BY, plus AX plus BC, with a little bit of a difference because these are vectors. And I just keep chugging them out. I'm going to get 9 terms here. Oh, joy. Here we go. AX times BX. Well, what happens when you take I hat times I hat? Well, we leave it as a dot product. Okay, that's how we handle multiplication of vectors. And then the hats are the vectors, and the other guys, AX and BX, are just normal scalar numbers. And you just AX times the BY, you're going to get I hat dot J hat. AX times BZ, I hat dot K hat. Out of room. Go to the next line. Now I do the same thing for the AY. I take AY times every one of the terms in the second quantity. AY BX, I hat dot J hat, plus AY BY, J hat dot J hat, plus AY BZ, J hat dot K hat. Oh, this is great. You should make a bumper sticker out of this. One more time through. AZ times all the quantities in the second, or all the terms in the second quantity. AZ BX. I'll change that. So this would be K hat dot I hat. I had these backwards, here's what got me, but that won't matter. AZ BY K hat dot J hat. AZ BZ K hat dot K hat. Whew, a lot of terms there. But we just said on the previous page, vector 1 dot to vector 2 is V1 cosine theta. Oops, forgot the V2. V1, V2 cosine theta. This works for unit vectors too. Works for any vectors. It'd be bad if it didn't. So it works also for unit vectors. So I hat dot I hat is going to be, well, what's the magnitude of a unit vector? It's 1 times 1. And then I take cosine of the angle between them. And when I'm dealing with two things along the x-axis, what's the angle between, you know, I hat and I hat? 0 degrees. That just equals 1. But if I look at the next term, I hat dot j hat, 1 times 1. Well, what's the angle between something along the x-axis and something along the y-axis? In this case, being the unit vectors I hats and j hats, it's going to be 9 degrees. And equals 0. So what happens is, so we're going to end our Friday lecture. So I hat dot I hat equals 1. J hat dot j hat is going to equal 1. K hat dot k hat equals 1. All other terms, I hat dot j hat equals I hat dot k hat equals j hat dot I hat equals j hat dot k hat equals k hat. Actually, they've all been taken up now, all the options, but if you want to, there they go. They all equal 0 because of what I just set up there with this, the perpendicular terms are going to be 0. Here comes the box. So you run back up this equation. Anytime there's an I hat dot I hat, that's 1. J hat dot j hat, that's a 1. And k hat dot k hat, that's a 1. All these other terms I just mentioned, other terms I did not mention, are gone. It's zeros. So A dot B equals AB cosine theta. That's our old definition. That's the old definition we had for work. Also equals AX BX plus AY BY plus AZ BZ. There's, so work equals that. If this for a force and that's a delta R, this would be work. Or we can use the components of the forces of the force and the components of delta R and also find our work. So I'll put the warning up here and we're going to end it. This is the scalar dot product. I'll put the warning, and then here it's last thing for the day. Keep all signs for components, positive or negative, for this guy right here. There's no angle dependence in a way anymore, but there still is. It's embedded in the fact that some of these components could be negative. Right? And you guys later on in math, or in physics we'll use it too, applies to any two vectors. Right. And that's it. we will use this. We're going to go back on Monday and do that problem number 2, which was a bear. Oh, no, I had to find my theta, but I mean, it may not exactly make any sense right now as we finish this up. But I had F, I had components, and I figured out delta R, which was our final in this case. There was its components. Heck with finding theta, I'm just going to multiply some components together, and it's going to give me the same answer. And if you don't believe me, you can do it over the weekend, or you can wait until Monday. I will redo that problem really fast because we want to figure out the theta. Sometimes it works out that way. Sometimes you don't have enough information. But if you've got vectors, if you got work as far as a force vector and a delta arc vector, boom, man, you got the components. You run through the scalar dot product without figuring out the theta. All right. But there's more we can use. Actually, it's very useful, and I'll show the use of that also on Monday. That's it, gang. I'll see you guys on Monday. Have a good weekend. Be sure to do that quiz.